Good day, everyone. My name is Josie Grace Lidoro.
I am Aimeline Buenafe.
And we are the reporter for the topic of mathematical investigation, process versus activity.
And mathematical modeling in the real world. So what is the objectives of our topic? At the end of the lesson, the students must be able to understand the different perception of mathematical investigation,
Explain what constitutes mathematical investigation.
distinguish what is mathematical investigation as a process and as an activity,
Explain the relationship of mathematical modeling and the real world.
So what is mathematical investigation? Mathematical investigation is defined as systematic exploration of open situations that have mathematical features, according to Bastow, Haggis, Kissane, and Mortlock of 1991.
And according to Lee and Miller in 1997, mathematical investigation wrote, investigations by their very nature demand an open-minded, multifaceted approach.
And according to Delaney of 1996, mathematical investigation believed in a more open spirit of the process-dominated investigation. Bailey of 2007, his idea of mathematical investigation is an open-ended problem or statements that lends itself to the possibility of multiple mathematical paths being explored, leading to a variety of mathematical ideas and or solutions.
And according to Ernest in 1991, describe investigation as the exploration of an unknown land where the journey, not the destination, is the goal. In other words, many writers believe that mathematical investigation is open with respect to its goal, processes, and answer. Many of them term investigation differently.
Orton and Frobisher of 1996 used the term problem and investigation to refer the task in their comparison between problems and investigations.
And according to Evans in 1987, used the term problem solving with investigation. Thus, the term investigation can refer to the task or the process of vote. And Evans in 1991 added, in mathematics education, there has been a fairly widespread adoption of the term investigation as a task itself.
Process versus activity. So this is the Venn diagram that differentiate the relationship between investigation as an activity and as a process. It is the investigative activity for open investigative task. So about the diagram, mathematical investigation as a process is the subset of the process of problem solving. But problem solving as a process is a subset of mathematical investigation as an activity. Therefore, distinguishing between investigation as a process and as an activity can help to clarify the relationship between mathematical investigation, problem solving, and problem posing.
About the mathematical investigation as a process, it occurs when solving problems with a closed goal and answers. And the mathematical investigation as an activity involves open investigative tasks, including both the problem posing and problem solving.
So what are the processes involved in mathematical investigation? So the first is organizing, then recording data, pattern searching, conjecturing, inferring, justifying, explaining conjectures, and generalization.
And the mathematical modeling is a process in which real-life situations and relations in these situations are expressed by using mathematics by Haynes and Crouch in 2007.
It is also a cyclical process in which real-life problems are translated into mathematical language, solved within a symbolic system, and the solution tested back within the real-life system according to Verschaffel, Greer, and DeCorte of 2002.
And the process of developing a mathematical model, a description of a system using mathematical concepts and language.
Mathematical modeling and the real world. So what is the relationship of a mathematical modeling in the real world? Mathematical modeling is commonly regarded as the art of applying mathematics to a real-world problem with a view to better understand the problem.
And mathematical modeling is capable of saving lives, assisting in policy and decision making, and optimizing economic growth. It can also be exploited to help understand the universe and the conditions needed to sustain life.
Mathematical modeling is also used to gain understanding of a real-life situation by learning how the system works, which variables are important in the system, and how they are related to each other. It can also be used to estimate quantities that are difficult to evaluate exactly.
In addition, mathematical modeling is described as conversion activity of a real problem in a mathematical form. Modeling involves to formulate the real-life situations or to convert the problems in mathematical explanations to a real or believable situation.
Another, mathematical models can help students understand and explore the meaning of equations or functional relationships. After developing a conceptual model of physical system, it is natural to develop a mathematical model that will allow one to estimate the quantitative behavior of a system.
And the most common types of mathematical model are equations and graphs. Other types of mathematical models fall into categories that include pie charts, tables, line graphs, chemical formulas, or diagrams.
What are the components of mathematical model? Mathematical model is composed of variables or decision,
Parameters,
constants and calibrations parameters,
input parameters,
data,
phase parameters,
output parameters,
and noise and random parameters. And the elements of mathematical model. Mathematical models can take many forms, including dynamical systems, statistical models, differential equations, or game theoretic models.
Other types of models can overlap with a given model involving a variety of abstract structures. In general, mathematical models may include logical models.
And in many cases, the quality of a scientific field depends on how well the mathematical models develop on the theoretical side agree with results of repeatable experiments. Lack of agreement between theoretical mathematical models and experimental measurements often leads to important advances as better theories are developed.
In physical sciences and traditional mathematical model, it contains most of the following elements: governing equations,
Supplementary submodels, there are two defining equations, and the second is constitutive equations.
and the next is assumption and constraint. It also have it two, which is initial and boundary conditions, and classical constraints and kinematic equation.
And classifications of mathematical models. Mathematical models are usually composed of relationships and variables. Relationships can be described by operators such as algebraic operators, functions, differential operators, etc., while the variables are abstractions of system parameters of interest that can be quantified.
Several classifications criteria can be used for mathematical models according to their structure. The first is linear versus nonlinear, then static versus dynamic, then explicit versus implicit, next discrete versus continuous, The fifth is deterministic versus probabilistic or stochastic. And the sixth one is the strategic versus non-strategic.
And how to create a mathematical model. In creating a mathematical model, we are given a word problem,
Determine what questions we are able to answer.
assign variables to quantities in the problem so that you can answer the questions using variables.
Derive mathematical equations containing these variables.
Use these equations to find the values of these variables. Okay, these are our illustrative example. A problem, a furniture manufacturer produces two sizes of boxes, large and small, that are used to make either a table or a chair. A table makes $3 profit and a chair makes $5 profit. If can you see M, small blocks, and N, represent in large blocks, are produced. How many tables and chairs should the manufacturer make in order to obtain the greatest profit?
So, in our illustrative example, we can see the large block, the small block. The large block the large block is composed of the table is composed of one large block and one small block. The chair is one large block and two small blocks.
Problem. Given M, small blocks, and N for large blocks, how many tables and chairs should we make to obtain the most profit?
In the table, the profit is $3, and in the chair, the profit is $5. Example, if the 12 small blocks and 12 large blocks, we can make 4 tables and 4 chairs. So, as we can see in our illustrative example, 4 large blocks and 4 small blocks in a table plus 4 large blocks and 8 small blocks in a chair is equal to 8 large blocks and 12 small blocks. The profit is equal to $3 times 4 plus $5 times 4 is equal to $32.
12 small blocks and 12 large blocks, 4 tables and 4 chairs. So the tables is $3 and the chair is $5. So we use the 8 large blocks plus 8 large blocks and 12 small blocks, so it's equals to 4 large blocks left. We did subtraction, and I can make two more tables. If I make one less chair, 3 chairs and 6 tables, increase my profit. 1 chair is equal to 2 tables. Profit goes up by $1. So the profit is equals to $3 times 6 for 6 tables plus $5 times 3 chairs. So the equivalent is $33.
In 12 small blocks and 12 large blocks, if 6 tables and 3 chairs, 9 large blocks is used and 12 small blocks. So, if we subtract it, 3 large blocks left. I can do it again. Change 1 chair into 2 tables, so 8 tables and 2 chairs. The profit is equals to $3 times 8 plus $5 times 2 is equal to $34.
For the 12 small blocks and 12 large blocks, 8 tables and 2 chairs. So we use 10 large blocks, subtract 12 small blocks, so there are 2 large blocks left. I can do it again, change 1 chair into 2 tables, 10 tables and 1 chair. The profit is $3 times 10 plus $5 times 1 is equal to $35.
So if I will use 12 small blocks and 12 large blocks, 10 tables and 1 chair, 11 large blocks plus 12 small blocks. If we subtract it, 1 large block left. I can do it again. Change 1 chair into 2 tables and 12 tables and 0 chairs. The profit is equals to $3 times 12 plus $5 times 0 is equals to $36.
And the 12 small blocks and the 12 large blocks can make the 12 tables and 0 chairs. If you use 12 large blocks and 12 small blocks, so no blocks left, so the profit is $36. Is this the best?
Now you try. 20 small blocks and 12 large blocks. How many tables and chairs?
Another 25 small blocks and 12 large blocks. How many tables and chairs?
So in the table, you can see that in 12 small blocks and 12 large blocks, not many small blocks is used. In small blocks that use 20, large block is 12, not many blocks is used.
So we have the variables. X is equal to number tables built and Y is equal to number chairs built. So M is represent to the number small blocks and N is represent the number large blocks. So how many can I build? So there is an equation here. X plus 2Y is less than equal M. I have only M small blocks. And X plus Y is less than equal to N. I have only N large blocks. Let's plot all possible choices for X and Y for a given M and N. And then we'll pick the X, Y that gives the greatest profit. Let's say, for the solving the equation, let's say M is equal to 12 and N is equal to 12 also. So X represents to the number tables, and Y is the number of chairs, N is the number of small blocks, and N is the number of large blocks. So X plus 2Y is less than equal. As can you see a while ago, X plus this one, X plus 2Y is less than equal M. So we substitute the M to 12. And here we go. So Y is equals to
Negative 1
half X plus 6. So the slope is negative 1 half.
X plus Y is less than equal to 12. Y is equal to negative 1 times Y is equals to negative 1x plus 12. So the slope is negative 1. So we want to find all possible X and Y that satisfy these two equations. So first, we have to draw the equality lines. So as you can see in our illustration, we have a graph. So now the inequalities, X plus Y is less than equal to 12. So which side of the line is this region? Let's check one point. In 0, 0, is 0, 0 in this region? Yes, when x is equal to 0 and y is equal to 0, then 0 plus 0 is less than equal to 12. So the allowed values of x and y are below this line visible points.
For the x plus 2y is less than equal to 12, which side of the line is this region? Region is also below the line, this one. Here, below the line. As can you see the graph? So,
So the allowed region for both inequalities is the common region or the intersection. Only x and y in this region are allowed. For m is equals to 12 and n is equals to 12. So in the graph, x plus y is less than or greater or equal 12 and x plus 2y is less than equal to 12.
now for x and y in this region, which one gives the highest profit? Profit is p is equal to 3x plus 5y. So y equals negative 3/5 x plus p over 5. Slope is negative 3 over 5. Let's plot the profit line. P equals 3x plus 5y. So as can you see the graph here?
Now for x and y in this region, which one gives the highest profit? Profit p is equals to 3x plus 5y. Then y is equals to negative 3/5 x plus p over 5. So the slope is equals to negative 3/5. The y-intercept is equals to p over 5. Along the profit line, all x and y gives the same profit. So the slope is negative 1, negative 3 over 5, and negative 1 over 2. In the graph, all x and y along this line gives the same profit p. So you can see it in the graph in y.
Now for x and y in this region, which one gives the highest profit? Profit p is equal to 3x plus y. So y is equals to negative 3 over 5 x plus p over 5, and the slope is equals to negative 3 over 5, and the y-intercept is p equals p over 5. Along the profit line, all x and y give the same profit. As can you see, the profit is increased. And the slope is negative 1, negative 3 over 5, negative 1/2.
Now for x and y in this region, which one gives the highest profit? The profit p is equals to 3x plus 5y. So y is equals to negative 3/5 x plus p over 5. The slope is negative 3 over 5 and the y-intercept is p over 5. So in the graph, you can see that the profit is increases. So what is the highest profit for those x and y in the feasible region?
Now for x and y in this region, which one gives the highest profit? Profit is equal to p equals 3x plus 5y. So y is equals negative 3 over 5x plus p over 5. And the slope is negative 3 over 5. And the y-intercept is p over 5. As can you see the graph, there is a profit increases. We keep moving the profit line upwards until the last visible point is touched.
Now for x and y in this region, which one gives the highest profit? Profit p is equals to 3x plus 5y. Now, y is equals to negative 3/5 x plus p over 5. The slope is negative 3 over 5 and the y-intercept is p over 5. So we keep moving the profit line upwards until the last visible point is touched. Now, it is the arrow in the graph shows that the line, and this is the only point, which is 12 and 0.
Now for x and y in this region, which one gives the highest profit? Profit is equals to p equals 3x plus 5y, and y is equals to negative 3 over 5x plus p over 5, and the slope is negative 3 over 5, and the y-intercept is equals to p over 5. So the greatest profit is achieved when x is equals to 12 and y is equals to 0. The profit is 36, as can you see the graph.
Now let's look at the case 1. M is greater than or equal to 2n. So n is less than m over 2. X plus 2y is less than or equal to m is equal to y negative 1 half x plus m over 2. The slope is negative 1 half. In the equation x plus y is less than or equal to n, y is equal to negative 1 x plus n. So the slope is negative 1. We want to find all possible x and y that satisfy these two equations.
Now let's look at case 1. M is greater than or equal to 2n. 2n is less than m over 2. So the x plus 2y is equals to m, and x plus y is less than equal n. We want to find all possible x and y that satisfy these two equations. So the feasible region, as can you see, where is the arrow? And then this one, the second line, x plus y equals n. This one, as can you see, the slope is negative 1 half and negative 1.
Now, in the same case, x plus 2y is less than equal to m and x plus y is less than equal to n. Now, plot the profit line with equation 3x plus 5y is equals to 5. In the feasible region, the slope, as we can see in the graph, is negative 1. The next in the graph, with the equation of x plus 2y is equals to m, the slope is negative 1 half.
Now let's look at case number 1. M is greater or equal to n, and n is less than m over 2. Now plot the profit line. 2x plus 5y is equals to p, and the slope is negative 3 over 5. So see the profit line. This one is the profit line, and the slope of the equation x plus y equals n is negative 1. And the slope of the equation x plus 2y equals m is negative 1 half.
So again, in the same case 1, x plus 2y is less than or equal to m and x plus y is less than equal to n. So we move the profit line up until it last touches the feasible region. So the same as what we have said before, the lines in the graph. The greatest profit line is shown in the graph. The slope of the two equations.
Now let's look at case number 1. M is greater than or equal to n, and n is less than m over 2. So the greatest profit is achieved when x is equals to 0 and y is equals to n. So as can you see, the greatest profit line is in the point 0n. And in the point n, the slope is negative 1. And the point m over 2, the slope is negative 1 half. In the equation of x plus 2y equals m.
So in the same case, the greatest profit is achieved when x is equal to 0 and y is equal to n. That makes n chairs and 0 tables. So again, we can see the graph, the same equation, slope.
For case number 2, now let's look at case number 2. M is less than 2n, n is greater than m over 2. So can you see the equation there? And then the graph. And the graph for the For the equation of x plus 2y equals m, the slope is negative 1/2. And for the equation x plus y equals n, the slope is negative 1.
So, at the same case, in case number 2, the feasible region is in y-axis. X plus y is equals to n, where the slope is negative 1. In the equation x plus 2y is equals m, the slope is negative 1/2.
And then, for the case number 2, the feasible region is, represent this one. Can you see the blue line here? This one is the feasible region. Note there is a new corner R. So there is a new corner R, and the slope of equation x plus y equals n is negative 1. And the slope of equation x plus 2y equals m is, the slope is negative 1/2. As can you see, the n and the m are meeting in the feasible, intersecting in the feasible region. So that's why we have the new corner, and that is letter R.
So, in the same case, in case 2, m is less than 2n, where n is greater than m over 2. X plus 2y is less than or equal to m, and x plus y is less than or equal to n. Now, let's add the profit lines. The highest one touches R. So, R is the point of x and y that has the greatest profit. So, as you can see in the graph, point R is the point where the equation x plus y is equals to n and x plus 2y is equals to m intersects.
Now let's look at case number 2, the same equation. What is x, y at point R? It is where the two lines x plus y is equals to n and x plus 2y is equals to m met. So they met, and we find that x is equals to n minus m and y is equals to m and minus 1, minus n rather.
So, in the same case 2, we have our answer. If m is greater than 2n, then we make x is equals to 2n minus m tables and y is equals to m minus n chairs. So, the problem that we have, how many tables and chairs should the manufacturer makes in order to obtain the greatest profit? So that's the answer. If m is less than 2n, then we make x is equals to 2n minus m tables and y is equals to m minus n chairs.
So we have the tables here, as can you see. This one is the tables for m is equal to 12, n equal to 12, m is less than 2n. For the tables, we have 0, 2, 3, 4, 6, 8, 10, 11, 12. And for the chairs, we have 6, 5, 4, 4, 3, 2, 1, 0, 0. And the profit is 30, 31, 29, 32, 33, 34, 35, 33, and 36. So this is the output.
So that is all for our report. Our formative assessment will follow. Thank you po, sir. Thank you, classmates.
Thank you, classmate, for
God
listening.
bless po.